shoveling snow through the forest doesn't sound as appealing now, as I'm a little bit older. And then even for my postdoc, I got to go out into these tall grass prairies in the central United States and look at how do things like bison affect all these different plant and animal groups. So I'm lucky I get to work in a lot of places and, you know, broadly ask these questions. Nope. Okay. And then ultimately, while I like doing science for its own sake, I find that interesting. I'm always interested in sort of like tying it back to these real world applications. So like how does what we learn doing science, testing hypotheses, lead to like better decision making, better management for things like conservation and restoring habitats that have been degraded, right? So it's always kind of in the forefront of my mind as I go through my research. So I'll give you a little bit of a background today to kind of give you some background information that I often think about that kind of frames and informs the questions that I'm asking. And then most of the talk will be diving in here to think about like how are fall and winter changing, especially in our neck of the woods here in the temperate forests. What are these seasons? What do they classically look like? And what might that be different in the future? And then finally, we'll kind of wrap up. I don't like to be super pessimistic about this, right? I think some optimism is really important and necessary. So we'll talk a little bit about how all of us can be part of the solution. And it'll hopefully make sense after we go through that talk. So let's start with some background, okay? So there's a lot of things about plants. I'm assuming you all like plants because you're here on a Saturday morning. It's really nice outside. So I'll share with you a couple of my favorite things that I find really interesting about plants. And so the first is this idea of like, you know, these plants, especially in places like central New York, they've got to go through a year. And that year looks really different seasonally, right? So in the summer, we're getting ready to go into this part of the life cycle, and it's really, really nice conditions, beautiful summer weather. So these plants are doing things like photosynthesis. They're starting to make their seeds. They're starting to produce their fruits. They can spread those seeds across the landscape. But then summer doesn't last forever, right? So then autumn comes, and we have things like what we call leaf senescence. So the leaves change color, and they're not really necessarily dying, but the leaves are sort of being shed seasonally for the year. And then those seeds are sort of leaving the mother tree and setting out on their own. And so once those leaves drop, then winter comes, and what these trees are mostly doing, again, they're not just dead, but they're actually sort of actively changing their physical properties and their physiology to make sure that they can sort of appropriately weather these cold winter conditions. They're doing things like actually making their own antifreeze in the winter, right? And that's like kind of an expensive, but a cool thing that they can do. And then spring comes, again, kind of like a nice thing that we're seeing now. And we see these leaves have to emerge at the right time. We have to start producing flowers so that we can start this process over again and make seeds. And this goes on and on. So this is what plants are doing under the hood. They're doing a lot of different things. And it's important that they're matching these right activities to the right time of year, right? So that's kind of a key thing that we'll talk about today. And what's even more impressive, if you think about all of these different things that they do, as animals, on the other hand, like animals get to move around and kind of pick where they're going to go. But plants have to do all of these things in one spot at the right time without moving. And that's a critical challenge. And that's something that's going to continue to become more and more challenging as the world changes quickly around these plants, right? So these plants, a lot of them live like trees for decades. And so you've got to sort of be in one place for multiple decades, tolerating all these changes. And that's a pretty difficult thing to do. So thinking a little bit more about these ideas of like plant life cycles then, we all see these big trees across the landscape, but we also know that then these big trees are out making seeds, which are going to leave and they're going to move around and establish on their own. They're going to make little seedlings, and those seedlings then are going to grow into their own plants and start that life cycle over again. So I always think this is really cool. And actually, most of my research studies what's happening with these seeds and these seedlings. And the reason for that is that a vast majority of these seeds and seedlings are never going to make it to become those mature parent plants. So a rough estimate, it varies a lot depending on where you are and what species you're talking about, but a rough estimate is that something like 5% of seeds will germinate into nice, healthy, living seedlings, 5%. And then of these seedlings that make it and establish, only 6% of those are going to turn into a mature plant one day. So what that means, if you multiply those two numbers together, every 10,000 seeds that are produced, only 3 are going to eventually become like a big mature canopy plant. So only 3 seeds out of every 10,000 that are made. That's a tremendous amount of mortality that's happening at this early, sort of life history stages. And so in order to understand how forests are going to change in the coming decades, we need to really zoom in on what's happening to these seeds and these seedlings. And so that's why my research mostly looks at that. I'm also going to talk today, though, about what's happening with mature trees as well. So again, 2 things that I think are really interesting that plants have to deal with. And then I also mentioned this idea of small mammals or rodents. And so I'll kind of introduce that now because it'll become relevant in the middle of the talk. So I got into research because I thought botany was really cool. I thought plants were really cool. I was lucky I had a great high school science teacher that really liked plants. I had an amazing mentor in my undergrad that really liked plants. And I never thought I was going to end up studying rodents of all things. But just because of the way that my path took me, I ended up in a lab where they studied rodents a lot and how rodents interact with plants. So I've gotten to know all of these nice little charismatic tiny animals running around the forest. And so they're really important in some sense because on their own right, like they have their own importance. They're one of the most diverse mammal groups. The only bats have more species diversity than the rodents do. But unfortunately, what's going on here is that across the world, we're really simplifying these rodent communities. So we're taking this really nice diverse group of animals that does a lot of things. We got cool like flying squirrels, or southern redback bulls that are like, eating mushrooms and stuff like that. And we're really simplifying those communities down to a handful of species. And these handful of species tend to be the really big enemies of plant species, the ones that are eating a lot of seeds. And they don't have very good immune systems. So they spread a lot of diseases to humans as well. So we're taking what used to be this like nice diverse group of animals, and we're kind of filtering it towards these couple of kind of, not our favorite species necessarily. And so now we're trying to wrestle with like, how do these different groups of rodents interact with plants and what can we do about that, right? So again, we'll talk about that a little bit more in the middle of the lecture. Okay, and so I'm going to try not to show too many slides today, right? I'm a professor. I like to look at slides and think about them, but I'll try to keep it, pretty tame here. I'll reel myself in. So I study ecology. I study things interacting. But remember, I also said that I work sort of at the point of conservation too. And any good conservation talk is going to have what we call a couple of doom slides to kind of frame the fact that like, hey, this is kind of a problem and we need to like be thinking about solutions for this. So this is one of my doom slides, so I'm sorry. So what I'm going to show you here is the idea that biodiversity across the world, you probably have already thought about this, but it's increasingly under threat, right? So I'm going to show time here on the x-axis. So years going back from 2020 to 2000, so just like the last 20 or so years. And the number of plant species in different categories of the IUCN red list. So basically listing things as endangered species or critically endangered or threatened or vulnerable species. And what we see is that even in the last 20 years or so, there's been a marked increase in the number of vulnerable, endangered, and critically endangered plant species. These are plant species specifically, right? So things are going on in our world right now in real time where we're basically doubling or tripling the number of species in these threatened categories. Right? And so this is like, now is really the time to start studying this. Really 20 years ago would have been the time to start studying it, but now is definitely the time to start studying it and start being able to form some solutions, right? And so why is biodiversity under threat so much? Like why is it really starting to increase the number of threatened and endangered species? Well, we live in this era that's characterized by the world changing really quickly. You might have heard the term the Anthropocene. It's like this fuzzy word, jargony word that's basically saying like, hey, our new geological era that we live in, not the Pleistocene or the Holocene, it's the Anthropocene. It's about people changing the world right now. And so there's 5 major causes of this change typically. The first 2 big ones are climate change and habitat loss, right? So we're rapidly changing the temperatures of precipitation that organisms have to deal with. And we're taking away or converting a lot of habitat into things like developed land or agriculture, something like that. So there's just less space to adapt, and there's a different climate to adapt to, right? And so we often, this is kind of another doom slide here, where we show maps of the world and how much the world is changing. And so you can just think of this blue to red gradient as like blue means there's little change or no change, and red means lots of scary change. And so you can see across the world here, especially in the tropics, but a little bit more creeping up into things like the Northeast United States. We're seeing more and more change. This is about climate specifically, right? So our climate is starting to really become novel and different, and these species are going to have to adapt to that. So we've got climate change, we've got habitat loss, but we also have things like pollution, we have things like invasive species, over harvesting, so like harvesting too many, hunting too many animals, harvesting too many plants, digging them up from the forest. These are all sort of 5 things that work together to explain why that biodiversity is increasingly under threat. And for my research, I think a lot about these two, the role that invasive species are playing and the role of climate change. Okay, so everyone take a deep breath after that. So, okay, we're gonna make it, right? Okay. So on that sort of backdrop, right, like thinking about these are really big, really important questions that we have to wrestle with. Well, a sort of interesting wrinkle on all of this is that species in these highly seasonal habitats, like we have here in central New York, they've got to adapt to all these different conditions, right? And so climate change, invasive species are sort of playing a role in that, right? So again, it's this idea that you go out into the forest and these plants can't move. Like if an invasive species comes into town, or it gets a lot warmer and we don't see as much snow, there's no option to pick up and move, right? So they've got to adapt, they've got to cope with whatever they're doing just by staying put. We've got to sort of help rearrange or otherwise, ameliorate the habitat around, right? And so I'll be talking a lot today about things like autumn and winter specifically. Those are my 2 favorite seasons to go out and collect data during. So let's talk about that now, like how exactly are fall and winter changing, especially in terms of climate change, especially in terms of invasive species, and what are we learning about the different ways that species can adapt to these changes? So I think one of the things that makes climate change so scary is that it's like really hard to like actually wrap your mind around what it looks like, right? You hear all of these things like, oh, there's like a 2-degree, warming in this number of years. And so you're like, okay, what does that mean? It doesn't seem terrible. If I like turn the thermostat up 5 degrees in here, that doesn't sound so bad, right? That doesn't sound like a big deal. And this is like a pretty coarse estimate. And so when these mean numbers are reported, so if you report something like 2 degrees Fahrenheit per century, that's how much the climate is warming. What we don't realize is that there's actually, if you look at that projected change across the map of the United States, there's hotter spots and colder spots, right? So there's variation from place to place. Not every place is going to warm the same amount. So like here in like Alabama, Mississippi, it's actually not changing that much. It's actually kind of staying constant. But up in the Northeast, that change is happening pretty quickly, actually, right? It's actually a hotter than average change. So these like single numbers of like 2 degrees Fahrenheit per century, it kind of masks a lot of place-to-place variation. But it also masks variation in like what climate change looks like at different times of the year. And this is where the idea of seasonality is going to come back in and really like my special interest in this. So what we've seen is that on average in New York, and this is data from NOAA and the DEC, our summers are getting about 1.5 degrees Fahrenheit warmer over the last century. So you're like, okay, 1.5 degrees Fahrenheit. It's not a huge amount, right? Fall is the same thing, right? So fall, also about 1.5 degrees Fahrenheit. But what about the winter? The winter is actually changing twice as fast as the summer and the fall is. So on average, our winters in the last century have become 3 degrees Fahrenheit warmer. So they're warming twice as quickly as the rest of the year. And so that's something that we're going to talk about what that actually does here in a minute. And then finally, spring, about 2 degrees Fahrenheit. So a little bit warmer than average, but still kind of closer to the summer and fall average. So really, what I want you to appreciate is this idea that like winter, that's where a lot of our climate change is actually going to hit. It's not that we're going to get these, at least in the moment right now, we're not seeing these massive heat waves and stuff that you're reading about in places like Western Europe. Right now, we're seeing our warming happening in the winter, and that's going to actually fundamentally change what our winters look like. You probably don't have to look very far in the past to understand what that's going to look like. So seasons they're warming at different rates, right? But how are scientists thinking about this? There's actually a strong bias if you go and look at when all of the scientific research is taking place, there's a really strong bias towards studying spring and studying summer, right? Part of this might be something like the academic year, right? Like professors often don't teach in the summer. And so we're free to go out and do research and look in the woods. And so, hey, we're doing a lot of studies in the summer. What we actually see, if you actually compare spring to fall, so there's a study that did this. They went and they just counted how many climate change studies were conducted in spring versus fall. It's about a 3-to-1 ratio. So there's for every 12 studies that are conducted, 9 of those are about the spring, and only 3 of them are about the fall, right? And so I think a lot of this stems from, just like human interest in this time of year. Everyone's like psyched to see spring colors, right? We're like so excited to see flowers blooming. We're starting to see the trees get their leaves back on. And so there's a lot of sort of good historical records of that, and we can compare to that from today's world. And so there's a lot of interest in spring, less so in fall. Fall has been kind of the middle child of climate change research. It's even worse though when you start looking at the summer to winter comparison. There's like hundreds of studies that are conducted every year about climate change and its effects in the summer, but only about 2% of all of the climate change studies are studying what's happening in winter. So think about what I just told you, that winter in our neck of the woods is warming twice as fast as the rest of the year. But we actually have next to no idea about how species are going to respond to these new winter conditions because we're just not studying it, right? So it's a huge hole in our understanding and our knowledge. And it's something that like my research with our students, we're trying to address this by sort of filling in this gap, right? We just need to know more about what's happening in the winter so that we can anticipate what's responding. So that background in hand, I now want to sort of talk about different ways. I'll give you a couple of examples of like how we can actually study what's going to happen under winter climate change. So the first thing, pardon another graph here. So this slide is hopefully communicating the idea that deep snow that accumulates in winter, typically in a place here like central New York, that's a really important habitat historically for plants and animals. So some of you might have a feel for this, but this graph, this is actually from Minnesota, and it's looking at temperature across winters. We've got December, January, and February here, and then we've got degrees Celsius on the y-axis here. So what this is showing is that if you just look at the air temperature, first of all, Minnesota, I'm from Wisconsin, so I can say this, right? So Minnesota looks like a terrible place to live, right? You look how cold it gets in Minnesota. So it gets down to like -30, -40 degrees Celsius. That's really cold. That's like sub-0 Fahrenheit temperatures. And so that's what's happening. This blue line is showing you what the air temperature looks like. It's getting really, really cold. But snow has these special chemical properties that actually let it act like a blanket in the winter if enough of it starts to accumulate. So while the temperature is bouncing down to like -40 in January in Minnesota, if you're under a little bit of snow even, you're only seeing like -10 degrees Celsius. And then this pink line shows you what if you're in like a really deep snowbank. It's actually pretty close to freezing, right? So it's a huge difference. You see like a 40-degree difference almost if you're under snow being insulated by that snow blanket, or if you're just exposed to the cold air by yourself. And not only is the minimum temperature here really low, but also look how much this that air temperature line is bouncing around. It's bouncing up and down. It's really, really variable. But look how flat this line is, right? It's really stable, nice, warm, stable winter temperatures, right? So if you're a tiny seed or a tiny seedling or a rodent or a fungus or any other small creature that kind of lives near the ground, in winter, you really appreciate having this nice blanket of snow around because it makes your life a lot easier, right? And in fact, there's all these amazing plants and animals that have adapted historically to like thousands of years of this nice, stable snowpack. And there's amazing plants like this glacier lily that can actually do photosynthesis underneath the snow in the right conditions, right? So even with trace amounts of light getting through that snowpack, that like around freezing, slightly above freezing in some cases, temperatures that you see in that pink line here will let this plant do photosynthesis under a deep layer of snow, right? So what we're trying to figure out is, okay, if you take that snow away, what's going to happen to these different plants, to the animals that they work with, that sort of thing. And so again, another good slide. So I'm just like really bringing the energy down on the Saturday morning. Here's a graph of how that snow cover has changed across the whole world. This is specifically looking at late snow, so like February, March snow in the northern hemisphere. And starting in 1967, there used to be about 31.5 million square kilometers of snow on average. And then follow that black line down, sort of cut through all that noise in the year to year. Some years are snow years, some years are less snowy. In 2021, 2022, on average, the new value is something like 28.5 million square kilometers. So we've lost about 3.5 square kilometers of snow on average across the world. And if you're like me and you're trying to figure out like, what this 3.5 million square kilometers even look like, it's about an Alaska and a half. So about in 30, no, sorry, what was that, like about 40, 50 years, 60 years, we've lost about a chunk of snow the size of Alaska times 1.5, right? So it's a lot less snow. Not saying anything about how deep it is. That's a lot of area that used to be covered by snow that's no longer covered by snow. And so what does this mean from a plant perspective? Like I said, you might think, well, snow means winter and plants like to grow in the spring. So maybe having less snow could be a good thing. And in fact, a lot of plants actually in their own, not brains, because they don't have brains, but they still kind of sense the world and react to it. A lot of plants actually kind of sense that same thing. They say, hey, I feel these warm temperatures a lot faster. So let me go ahead and like put my flowers out, put my leaves out. But what this leads to is what we call a false spring, where these leaves, these floral tissues, things that are really sensitive to cold temperatures are starting to come out too early. It's a false start essentially for those, right? And so they come out too early, and then there's some snap back where like freezing temperatures return, right? This is why we don't plant our gardens here in April, even when it's 80 degrees and feels really nice, right? Because we know that there's always the risk that frost could come back before the end of the year, right? And so these plants are subjected to that. And see here, you can see in this nice cherry tree that these flowers have actually, they came out, they started to like advertise, their floral structures and try to bring in the pollinators, but then they ended up dying because they came out too soon and they got hit with a frost event and they're not really well tolerated. They don't tolerate that frost very well, right? So we typically think of these false springs as bad for plants, right? We don't want to see them exposed to these. And so now I get to tell you a little bit about one of those studies that I did when I was in graduate school. We were thinking about these false springs, and we said, hey, that's kind of an interesting idea. And there's a lot of species out there. We don't know which species might be the most susceptible to them. We don't really know what the effects might be. So I took 4 species of trees that grow in Wisconsin, where I was doing my PhD work. So baldwin fir, that nice little, some people use it as a Christmas tree. Red pines, white pines, so 2 important, economically important conifer species, and red oaks, kind of like a common feature of a lot of forests in Wisconsin. And so we took seedlings, we grew little seedlings of all these tree species in a greenhouse, and we actually did something pretty cool. We have a device that looks like a refrigerator. It's like this. It's a growth chamber, and you can actually program it to get really cold and mimic the effects of these false springs. So imagine you could program your refrigerator to be a really nice comfortable temperature, like 15 degrees Celsius to about like 40, 50 degrees Fahrenheit for a while. And then you could program it to snap back down and freeze. That's what we did with these growth chambers. And we put these different plant species inside them to try and identify like which ones might be a little bit more resilient to these false springs and which ones might be in trouble a little bit more. And remember, I told you something about me. I don't like just thinking about like the climate angle. I'm always thinking about how plants and animals might interact with each other. So then on top of this, we subjected these plants to a second stress, which I'm going to show you a picture of a horrifying herbivore species. Ready? So my pair of scissors that I mimicked. I pretended to be an herbivore in the greenhouse, pretended to be like a deer or a rabbit or something, came and like clipped off a certain amount of that stem tissue in all these plants, right? So then we could actually see which ones do worse with just the cold stress, and then maybe which ones are susceptible if there's multiple things attacking you, right? Let's say if you're attacked by a bad climate and by an herbivore, does that mean you're really in trouble? So these are the types of questions that we were going after. And so here are some results that we found. So on the x-axis here, I'm just going to show you like the different false spring treatments. So the 8 degrees C, that's about 40 degrees Fahrenheit. That's like a nice comfortable temperature. So that was our control. Like the temperature went up to spring temperatures and stayed at spring. There's no false spring in this rightmost category. And then the -8 and the -16, those are 2 different treatments where the temperatures return to freezing. So just a little bit of freezing in that middle category, and all the way on the left, that was the most frozen, the worst fall spring the species could tolerate. And so what we did is we looked at sort of how those species survived into the summer. So like if you're exposed to one of these three treatments, how well do you survive? And then also how much do you grow? So higher values here means that those seedlings were able to bounce back and grow better. So what we actually find is that these points are all kind of like pretty similar to each other. There's really no consistent difference between those 3 points. So the 4 species that we looked at, balsam fir, white pine, and red oak, the optimistic news is that, hey, if we expose you to at least one fall spring, they all survived pretty well. So like they had about 90% survival. Good. It's in a greenhouse, so it's kind of simplified. There's not a lot else going on. But that suggests that these 4 species might not face a lot of death from these fall spring events. So that gives us some optimism right there. But the bad news was that if you were exposed to the worst fall spring, you didn't grow hardly at all. So there's very, very little growth going on in those groups. So they survived, but they didn't grow very well. And you need to grow in order to ultimately become one of those plants that reaches the canopy, right? But if it's just kind of a mild fall spring, then you're kind of the same as the control group and life is okay, right? So the take home here is that those fall springs for these 4 species we looked at, they did reduce seedling growth, but they didn't reduce seedling survival. So it's kind of a mixed bag there, right? And so now this figure is going to get a little bit more complicated, but I'll walk you through it. And I'll tell you the punchline first. The punchline is that if you combine that fall spring with an herbivore attack, that actually does lead to bad things for the season, right? So we looked at this. I'll show you 2 species that we looked at this for. The first one is these red pines over here. So again, we've got survival on the vertical here, and then our same temperature treatments on the X. But now we're going to break into 2 groups color coded. The blue circles will be seedlings that just got eaten a little bit by my scissors, and the orange triangles will be seedlings that got eaten a lot by my scissors. So a really extreme herbivore attack. And what we found was that generally there's no, like whether you got eaten by an herbivore or whether you were in the 8 or the -8 treatment, still lots of survival. Survival is pretty high across the board. But what we see here is when you start putting these multiple stresses together, this is a seedling. Remember that this species wasn't affected by the really cold climate just by itself. The fall spring by itself didn't affect survival, but now throw an herbivore attack like a deer coming to eat you on top of that, and suddenly survival is basically 0%, right? So this suggests that if we're going to help species weather climate change, it's not just about the climate, but let's also make life easier for them. Maybe throw out some deer fences or something like that to protect these species. So when they're stressed out, they're not going to get pushed over the edge, right? Interestingly, we did the same thing with the northern red oaks, and it actually didn't matter. Attack them with scissors, don't attack them with scissors, freeze them, don't freeze them. They were pretty resilient, right? So this red pine responded really poorly to the 2 stresses together, and the red oaks, they're like, yeah, we're good, right? So that was kind of an interesting and exciting result for us that, okay, red oak might be a good species when it comes to these stressful climate conditions. It might be doing okay. And so we were really curious about this result that, climate change by itself might not do a lot to decrease survival, but multiple stresses can, right? And we were really curious, why did those red oaks do better? Well, one of the reasons why is we thought they have these big tap roots, right? So the other species have really kind of like wiggly, fibrous roots that just kind of branch really shallowly. And these red oaks have a nice thick tap root. So if you're freezing the soil, this big fat root might not be so susceptible to damage, but those little fibrous roots are more likely to freeze and crack and be affected by that freezing soil. So that's maybe one clue to why that species did better. So another thing that we thought about too, though, is okay, this is an indoor lab study. You're holding a lot of things constant. The world is a super messy place, right? So does it actually mean anything out in the real world? And I don't know if what I'm about to tell you guys is fortunate or unfortunate. It's being in the right place in the right time for me, to do research and answer questions, but it was not a great thing to happen necessarily. So this is a map of Wisconsin, and the star here shows Madison, where I went to graduate school. And now we're going to talk a little bit about Arboretum. right? So these arboretums and what they are and like how they're actually really helpful for studying things like climate change. So this is a map of the University of Wisconsin Arboretum in Madison. So it's cool because these are all individual trees, and look at how many different types of trees are all growing in one common environment, right? So we've got magnolias, we've got crab apples, maple trees, ginkgos, pines, firs, all these different species in the same place at the same time. And so this is actually a really powerful tool to say, hey, if there's like something weird that happens in this environment in a given year or given place, we can actually look at how all of these different species from across the world are going to respond to it or not respond, and we can learn something about the different species and their responses to climate change, and try to make some predictions about like who's going to be a winner or a loser given that climate change is happening. So this is kind of the setting for the next story that I'll tell you about. So the weird event that happened, this is in 2017. It was actually probably the nicest February that Madison, Wisconsin has ever seen in historical records. So this figure is showing sort of like time on the x-axis again, so February, March, April, May. And then this first row here is like when historically, and this is like looking at, all from 1966 to 2016, when historically you see 6 consecutive days at 15 degrees Celsius, about 45-ish degrees Fahrenheit. Sorry, or 60 degrees Fahrenheit. And then when do you see the first day of 70-degree weather on the top, right? So basically imagine the week that we just had here in central New York in February. And that's what happened in 2017, right? We basically had an unbelievable stretch of weather in February where it was almost a week of 60-degree Fahrenheit. And we even broke into the 70s in February in Wisconsin. Wisconsin, in case you've never been, it's a lovely place. It's very cold in the winter, right? It's colder than central New York is. And so to have that week of weather in February, we thought, man, that is a false spring, right? Because and it did in fact. So we went out, we collected a whole bunch of data, saw how all the trees were responding, right? So we actually tracked are the buds opening? Are they closed? Are things starting to flower early? And we did this for 101 species in the Arboretum. And as we were rushing around collecting data, it started to ice and snow on us, right? So it definitely was a false spring where this spring weather occurred early and it dipped right back down to freezing temperatures. And so what we found was that of the 101 species that we looked at, almost 50% of them started to actually grow. They actually started to put leaves out. Their buds were opening. Those buds are normally a nice way to protect leaves and vulnerable tissue during the winter, but they were opening up and sort of putting their vulnerable tissue out and exposing it to the air. And so almost 50% of those showed that they thought it was spring. They thought it was time to come online and start growing. And we were able to luckily look, because we had more than 100 species at this arboretum to look at, we were actually able to see hey, are there any generalities and which ones were less likely to be tricked by this fall spring and which ones were more likely to. And what we found is that species like oaks and beeches, almost none of them got started during this fall spring. But things like maples and cherries, most of them had started to put their leaves out. And this actually maps on really well what we know about these species and the strategies that they use to navigate the seasons. You have to go right outside of the Science Center right now, and you'll see that these maples and cherries are some of the first ones responding this spring. Go look at those big oak and beech trees, and they're not even really close to getting started growing, right? So we kind of know that if you sort of know these trees and their tendencies, but we were able to say hey, in a real world context where you're exposed to this novel, this new and different winter climate, yeah, these ones are probably going to be okay. They're not going to get tricked, but these ones are. And so these ones might be the vulnerable species, right? So that's my winter side of the story. I'm going to quickly tell you about some really interesting work that we do to understand autumn and how autumn's came too. And here I'm going to deviate a little bit from the climate change angle. I'll come back to it in a little bit. But I like to show this slide because is anybody fall's my favorite season? Fall's my favorite season for sure. I like to talk about how in the Adirondacks you can see fall from space. So this is a satellite photo, a satellite flying over the Adirondacks, and it's such a dramatic and pronounced season. You can zoom out all the way up in outer space and watching this happen. So it's a really charismatic time. It's an awesome time. There's a lot of cultural importance, I think, to people that live here with this time, a lot of tourism that happens. But more and more, we're getting these invasive species that have pretty weak fall color, right? So this is an invasive buckthorn plant growing on the side of a forest here. You can see this is in the fall where all of these oaks and maples and hickories that are sort of growing above it are changing colors. They got these nice red leaves. They're dropping their leaves. They're getting ready to. And buckthorn's like, nah, I still got green leaves. I'm still doing photosynthesis here. And it turns out this is one reason why these plants are actually invasive in the first place. Their growing season, their leaves can actually tolerate cold temperatures pretty well. Their growing season is almost 80 days longer than most native plants. They can keep their leaves come online earlier in the spring. Again, go outside, go find some buckthorn or some honeysuckle. You'll see their leaves are almost fully out. And so they come out really early in the spring and they hang on to them really late in the fall. So like honeysuckle, one of these plants, they're from places like Siberia, where it's really cold. It has cold variable air temperature. It's used to it. It doesn't mind it. So it's evolved to sort of have this nice green extended canopy, right? So these plants are really green for a really long time, kind of counter to our nice fall colors that we like to see. And so that has a big direct effect on these plants. They're able to do more photosynthesis for longer, make more energy, but it also has rippling effects across the forest food web. So I get to talk about rodents now, right? So what I'm going to tell you now about mice is something I never ever thought about until I started studying this. But not only is that green canopy nice for photosynthesis, it's awesome mouse habitat, right? So imagine get inside the brain of a little mouse or chipmunk running around the forest floor. If you've got these nice green leafy canopy overhead, something like an owl that wants to eat you, wants to swoop in and find you and eat you, it's going to have a harder time doing that when you're kind of shielded by a nice thick canopy. But when those leaves are off the trees and you just have bare trees and a lot of open space in your canopy, that owl is much more likely to swoop in, find you, take you out, right? So if you're a mouse that eats a lot of plant seeds, this invaded habitat is really nice for you. And you're going to be able to actually eat a lot more native plant seeds, kind of accelerating how well this invasive species can do because you're actually taking out its competitors for it, right? So this is how we see sort of native animals that are sort of being co-opted by these invasive plants to change their behavior and help the invasive plant out by eating more of the competing species. So this is a sort of a study, or it's something that we started to notice, and we wanted to study it a little bit further. And so, just to illustrate this as well, that extended green canopy for buckthorn, so this is what an uninvaded forest typically looks like. You've got leaves coming out like April into May, and then falling starting in October, going into November. But in a buckthorn forest, that window where the leaves are on, it comes out much earlier in the spring and stays on much later in the fall. And so when I was doing my PhD, one of my lab mates studied this. This is Christina Bardowitz, and she's now a postdoc at Washington State University. And so she was looking at how many seeds are removed and eaten by little critters like mice and chipmunks in the forest. And she studied that in July, September, and November. So basically this period where everybody's going to have a nice canopy. Here, the natives are starting to get ready to drop their leaves, but buckthorn isn't. And then by November, all the native leaves are off the canopy, but buckthorn still is like hanging on, doing photosynthesis, providing that canopy, right? And so what I'm showing you here are red maple leaves, these little red maple helicopters that you might see, like how many of those get eaten by mice. And there will be two sets of bars, one where our cathartica is the Latin name for buckthorn. So the gray bars are places where buckthorn is, and the white bars are places where buckthorn was chopped down and pulled out of the forest. And so what we see is that these bars are the same height in July. So in July, it doesn't matter if you're standing in the forest with buckthorn or without. There's a lot of red maple seeds being eaten. But normally, in a place without buckthorn, that's the number of seeds getting eaten would drop down in September and November when those leaves start to drop and the mice are more scared of their predators. They're going to eat fewer seeds. But we see that it just stays really constant if you have buckthorn there, right? So there's a lot more native seeds getting eaten where we have buckthorn, and that's especially the case in fall because those mice continue to be protected from their predators. And so what I wanted to do is I wanted to sort of follow up on Christina's study and say like, okay, can we learn anything more about like how exactly these mice are responding and changing their behavior? And so this is what my study sites look like. So this maybe illustrates what I was talking about a little bit better. Here are these sites where buckthorn was pulled out. This looks like somewhere you might want to like hike through. It looks very nice. This is somewhere where you didn't pull buckthorn out. You don't want to walk through that. It's very thick. You're going to get lost. You're not going to have a good time. But if you're a mouse running around down here, you love it because nothing is ever going to find you, right? It's like, which is way too thick. You can have a field day, you can go nuts. And so this is, I think, I told you a little bit about the shoveling snow out of the woods and how that was a kind of a silly idea. This might be the second silliest idea I've ever had for doing research to learn about this stuff. We wanted to know, like, okay, when a mouse takes a seed out of like our buckets of seed, like where do they take it? How are they behaving? Are they eating it? Are they not eating it? Like, can we just learn a little bit more about like what the mice are doing? So my advisor was like, hey, you know what a great idea would be? Like put these little metal tags into red oak seeds, into acorns, and then go around with a metal detector and like try to find them. Which I don't know if anybody has like metal detecting as a hobby, but trying to like swing a metal detector through that, it was horrible. It was not a fun time. So like we learned a lot, and I'm like glad that we did it. But like it's just I laugh about it now. This is the thing that I once metal detected through the woods looking for these tiny seed tags. But we did learn something, so it's okay. So we tracked these seeds and we wanted to learn like, okay, how far did they move? Were they eaten? Were they not eaten? And then we also made notes about like, okay, what was the environment like where we found that seed tag again? And I'm glad that we did that last part because it turned out an important part of the story is actually what we call woody debris. So something like this in the forest where a tree fell down or a tree limb fell down, this is really good rodent habitat. They tend to like this habitat. And so we noted whether the seed were recovered or the seed shard, like the seed that gets eaten, it looks like that, whether it was recovered next to a big log or something like that. And what we found was that in sites where we pulled out the buckthorn, basically all of the rodent activity was around these logs, right? So these logs provide like a nice little feature that you can hide under. If you get scared and think like a fox or something's gonna come by, I can like dive into the little gap here and feel safe. And so they were mostly restricted to using these woody debris pieces, and they didn't move very far across the habitat. They kind of like would take the seed out of the bucket, run to the closest piece of woody debris, and eat it. That's what we found. But imagine that you could see a piece of woody debris down here in the invaded site. We actually found that like in the presence of buckthorn, the mice and the chipmunks, they stopped caring about this sort of classic habitat feature. Like we don't need this piece of woody debris because look how great the rest of the habitat is. So they spread out, they're using all of the habitat, and they're basically just moving really far around and taking the seed wherever they want to. And so this is bad from a conservation standpoint, because if we think about this, in this scenario without buckthorn, you kind of have the small mammal activities restricted to a handful of places. So if a seed lands here or here or here away from a piece of woody debris, like you might make it, right? Like the mice and the chipmunks, they might overlook you, they might not search too hard for you. But here, where you're not relying on woody debris as much, it's just kind of a mouse free-for-all. Like the mice can do whatever they want, whenever they want, and they're more likely to sort of pick out every single last seed and eat it, right? So that taught us something about how these invasive plants can kind of change the behavior of native animals to the detriment of the native plants that we want to promote. And I like to keep thinking about this. So like I like to eat food. I think that's where this comes from, right? But like I love to think about like what are the factors that cause animals to eat more or less plants. And so I have a student right now, Maddie Vavra in my lab, who's doing their senior thesis project on trying to like come up with better ways to quantify this. Maybe you've been out hiking in Rogers Glen and seen something that looks like this. I don't know if anybody has ever noticed these. These are what we're workshopping this name. It's not a done deal yet, but we're calling them the temporal rodent activity and seed predation hazard, or trash cans. It's literally just a trash can with a trail camera pointed on like a board full of seeds. So what this allows us to do is we can actually see which species, mice, chipmunks, voles, flying squirrels, red squirrels, we can actually see the different critters coming in. We can measure like how long they're hanging out there, like how long they feel comfortable eating, and which seeds they're going after here. So rather than just like putting out a bucket of seeds and coming back a week later and seeing like, okay, there's like 10 left, we put 20 out, so like half of them disappeared. Now we actually know like which individual seeds were taken by which species of animal. So it gives us a lot more finer scale information to start actually measuring these different plant animal interactions. So it's very exciting. And so I'll pivot now and I'll just come back to tell one last story about autumn changing and winter climate. Sorry, not winter climate, but autumn climate. So there's a big debate in the world right now. If we think about climate change, we think about what's happening in the fall. Remember I said, it's not an especially big time of warming. It's about average warming that we see in autumn. But the big debate is like, okay, how are plants exactly going to respond to warmer temperatures further across the year? So historically, if your growing season runs from something like May to October, one school of thought says, well, maybe as November warms and April warms, you're just kind of going to like have a longer growing season, right? Kind of like what you see, south of you. So that's one school of thought. And there's some evidence that that might be the case. But recently, there's actually a second school of thought that's maybe a little bit more alarming. And that is, well, maybe you don't get a longer growing season, but maybe it just shifts earlier. And the reason for this is that as a plant, you only have so much space to store the energy you make, right? So most of the sugars and stuff that plants are making in photosynthesis, they get stored in the roots. So you kind of run out of storage space at some point. So it wouldn't necessarily make sense that you would continue to like be growing and putting leaves out and doing photosynthesis if you don't have anywhere to put that extra sugar that you would make. So maybe they're just like, okay, I got started earlier, and then I did what I have space to do for the year, and I'm actually going to drop my leaves earlier than I did historically. And so this is actually, it's both, there's evidence that supports both of these two ideas, but there's so much that we don't know about like which one might be more common, which species and which places might do earlier growing season versus a longer growing season. There's a ton of work that we need to do to figure out what might be happening. And so we don't know, like, is it going to shift climate change? Is climate change going to shift the season earlier or later? And this is where the Hamilton College Arboretum comes in. And specifically one of the classes that I teach, my upper level seminar course with Hamilton students. Forgive this really ugly map that I just auto made in Google Maps. But the Hamilton College Arboretum, it's got 485 trees. Sorry, it's 2,500 some trees. My class looks at about 485 of those trees, and that covers about 125 different species, right? So we're taking basically a similar approach to what we did at the UW-Madison Arboretum, where we looked at every individual tree and said, like, hey, what is it doing right now? Are the buds on it? Are the buds not on it? In our case, we're looking to see, like, do the leaves change color? Are the leaves still green? Does the tree have fruits on it? Does it not have fruits on it? And every different tree here is one of the trees in our data set, and all the different colors correspond to different species of trees. So my students and I in the fall, we're out there covering a lot of ground. Every week we go out, we kind of monitor the status of these individual, about 500 trees across campus. And we do this according to sort of like what's like a nationally standardized protocol. It's not, we didn't just like make this approach up, but we have sort of like, we're plugging into what's called the USA National Phenology Network, where anybody can sort of sign up to do this. And you can actually like find your favorite tree and say, hey, what's going on with its leaf buds today? What's going on with its leaves? Are they colored? Yes or no? Just making those sorts of observations. And that data gets plugged into a big national database of individual trees being monitored across the country. And so here, you might not be super excited to see this until I explain it. Congratulations to the first people to see these data. This is from the first year that we collected these data. But what we were able to do is we're kind of showing that we can quantify that transition from the growing season into fall for different species. So here what I'm showing you is like, again, time on the x-axis, so like what week of the year, and what percent of the canopy is doing different things on these different trees. So for sugar maple, for black walnut, northern red oak, and little leaf linden. These are the four most common species in our arboretum data set, right? And so what you actually see is that this green line is like how many of the leaves in the canopy are green. And the gold line is how many are changing colors, starting that fall transition. And so you can see, for example, you can kind of say, hey, at this date right here, like early October, this is when the sugar maple transition starts to really kick off. This is when like the peak colors for sugar maple start to occur. And that by itself isn't super exciting until you look at like, hey, how does that compare to another species like northern red oak? So see, this is a very messy transition. It's a very back and forth transition. There's kind of a long window in which those green leaves and color leaves are mixing. And here for northern red oak, it kind of stays really green for a long time, and then it's a sharp transition. Right? Same thing for this little leaf linden. So it's pretty much all green until like late October, November, and then its leaves change really quickly. And so this is 1 year of data. This by itself isn't going to tell us a ton, but what we're hoping is that I teach this class every single fall. So 5 years from now, we'll have done this 5 times. And we can start to map, like, when is that transition date from colored to green leaves? When does that transition date happen? And like, how does that correspond to something like how hot it was, or how dry it was, or whether there was a gypsy moth outbreak in a given year? So all of these different things. So students are actually doing projects with these data to try and like be part of the solution and understand what are the drivers of this fall to winter transition and how different species might do it, right? So we're really excited about this. It's a project that's still in its infancy, but it's going to be really cool. And it's a way for students to actually be actively involved in this sort of climate change research, right? And so now what I want to sort of make you aware of is that you can actually be part of this too, right? So this isn't something special for my Bio 419 students at Hamilton College. This is something you can actually go online. You can Google Nature's Notebook. That's the name of this program. And it's an app that you can download on your phone. And maybe you have like a favorite tree in your yard, or a favorite tree that you walk by on your way to work or something like that. And you can actually do these same sets of observations year round, right? And so you can do things like say, hey, when does it flower? What was the first date that I saw it flower? In how long do those flowers stay on? When did I first see a maple helicopter coming down in my yard? All sorts of those questions. And that might seem really trivial, but this adds up really quickly. We call this a community science approach, right? Because there's only so many scientists in the world that can like look at data at a given time, but we can all be sort of part of this process of doing science together. And so across the world right now, there's something like 60,000 people that participate in this Nature's Notebook program. And so they're all sending their observations, something like 100,000 regularly monitored individual organisms, both plants and animals. Maybe you have a favorite bird season or a favorite bird and you want to be able to say like, hey, this is the day that I first saw, red-winged blackbirds in my backyard, something like that. And that's a helpful data point. So there's something like almost 2,000 species covered in this database, and it's led to more than 100 peer-reviewed scientific studies already. So scientists are using these data to say everything from like, how do invasive plants work? So remember I said that like 80-day longer growing season for buckthorn and honeysuckle, that was estimated using Nature's Notebook data, right? Like that's how we have a number for that. It's from everybody going out and looking at buckthorn or honeysuckle in their backyard. It's used to study things like species responses to climate change, and also things like monitoring allergy season. Like, is allergy season shifting or changing due to climate change? We can actually start estimating those from pooling everybody's observations across the world. Right. So this is a really powerful thing that all of us can be a part of, and that's a cool opportunity. Okay, so I've talked your ear off for an hour. Sort of 3 take-home points that if you want to like hang on to these, this is what we talked about today. So we talked about how the world's changing, and every season within that change happens really different, right? So we can't just do all of our research in the summer. We have to do research in the summer, in the fall, in the winter, in the spring. And we saw that there are some plants that can actually cope pretty well with these changes, but others won't. And so a big part of what we do as ecologists and scientists is trying to understand which species fall into which group. And then finally, like identifying those winners and losers, it can take a whole village, right? So like having more and more people in the community help collect these data through things like Nature's Notebook can actually be a real benefit and a real powerful tool to fight climate change. So thanks very much to all the people that have supported me. Thanks for being here today. I think I've got a few minutes for questions, so appreciate your time. Hopefully you learned something. Yeah.
There's a lot of speculation, for instance, like the sugar maples are declining and they're moving north.
Right.
Relative to what you told us today, that would seem like it would be an evolutionary thing. In other words, they would die off and they wouldn't reproduce, so they would become more numerous. Is that or there are other things that they're considering that.
Right. And so typically, when we think about how species might respond to climate change, there's typically three ways that can happen. The first is what we call migration. So kind of like what you're describing, the geographic area that you find the species moves towards the pole. So in our case, like north. And so that's what we see sugar maples doing a lot of migration. Those seeds, the little helicopter seeds, move pretty well actually. So they can blow in the air, they can move a pretty far distance. So that's a good option for it. For species that that's not the case, you might see adaptation. So something like evolution, sort of like shape, a better response to a warmer environment, or change the time of year that you come out and push these out. And then if you can't migrate and you can adapt, then that's when we start to see species go extinct. That's sort of the third option. So what we do also is try to think about, like, okay, are there spots where we can maybe like introduce sugar maple and say like, hey, this is maybe a good habitat for it, where it wasn't previously, or new habitat for it. So yeah, absolutely, that's something that we definitely think about. But unfortunately, it looks like Canada is going to have more of our sugar maples in the summer. Yeah.
So, if you're trying to plant native species in an area, given changing climate, should you actually be looking at plants from further south? That is actually native to your area or not?
That is such a great question. And this is something that we argue about, and people have different feelings about it. So there's I can't stand up here and say, this is what science says we should do, because people just have different interpretations of it. I can tell you that the group that I work with here on campus that's running a lot of the reforestation that you might see, this is something that we've thought about. Because to us, we see that there's a certain amount of warming, at least at the network. So if we're planting things like a lot of sugar, if we're only planting like sugar maples and beeches here, are we really doing anything if those trees aren't going to be doing well in 50 years? So we started planting, along with what we would expect to see here, more things like oaks and hickories that you find further south. So that's something that I do when I think about planting. Some people feel really strongly that we should give what's here currently its best fighting chance, and there's nothing wrong with that mindset. But yeah, I think if you want to plant native plants with that in mind, that's also a perfectly reasonable thing to do. Yeah. So I wish it was as easy as saying this is the right answer, but so often we're not actually sure what exactly that is. But I would say, plant with knives or things that grow slightly different.
I suppose it might matter how long lived the species is.
So that could also matter too. Are you talking about like, ground cover plants that live, like annual plants, or, things that are gonna live 10, 20 years versus like a 200-year-old, 300 or 400-year-old tree? Yeah.
Another possible complication of that would be that because there's so much more variability now, species native to a certain area, dealing with that, and the species in a more temperate, moderate climate, warmer climate, they're still subject to the difficulties of the extremes. So with variable weather, they don't have the defenses or the accommodations to handle that change. So if you just bring in more southerly plants, they would be exposed to those variabilities.
Right.
In a partial way.
Right, exactly, because well, central New York has certainly been a place of like deep snowpacks historically. If you look at somewhere like Virginia or Maryland or North Carolina, like those are places where you maybe didn't ever have historically consistently deep snow as we have. And so maybe those plants and animal species, so like you're saying, a more extreme or more fall springs or something like that was part of your environment historically. So you might have more tools that help you navigate that. But certainly could be the case. Yeah.
We have a question from Zoom.
Great.
So we're trying to get rid of buckthorn, but also to replace them with native understory trees. Will those be better at letting the owls get the mice because their foliage season is so much shorter than the invasives?
They certainly could be. I think my answer would be that, generally mice won't care about what specific species it is necessarily. But if there's a really dense growth year round, whether it's native or non-native, the mice will probably use it as habitat. Yeah. Hopefully that addresses the question.
For those of us who are addicted to watching nature programs, we learn slowly about the benefits of ecology of fear that apex predators in a good supply can rebalance everything, including botany as well as other animals. Is there, in your presentation, could you say there's a parallel example of ecology of fear if you look at, say, the heavy snowfalls and the cold temperatures as being the fear rebalancer?
No, I think there's a parallel to it, and I think, I didn't talk about it a lot also, but it's complicated. I do also study how things like mice respond to variable snowpack themselves with their behavior. And what we actually see is that with the predator idea, there are some predators like an owl that if a mouse is under deep snow, an owl can't do much to get at you. But something like a fox or a weasel might have more advanced tactics that can get you. So it depends on which predators are around and how the mice would respond to having that protected, because it's not just insulating them, but it's also a protection from predators, snow historically. But the double-edged sword there is that for something like a mouse, deep snow also makes it harder to maybe find new resources and replenish their food source in the world. So we've also done some studies, I didn't talk about them today, but when you do something like shovel snow out of the forest, how does it change A, how scared the mice are from their predators, because now they're more vulnerable, but B, can they kind of compensate by getting more food? And they find food easier in the environment. And what we found was that generally they tend to care less about the predators and they tend to forage more on things like seeds. So they'll eat more seeds if you take snow away. They can, our interpretation was they could find it more easily. So there's a lot of complex interaction being mediated by snow between plants and mice and other rodents and their predators. And so, when you take that snow away, you're changing all of those things at once. And it's actually really hard to try and untangle all of
Could you also extend the parallel to plants, and particularly with cold weather? And the cold weather is the equivalent of the apex predator. And that so that at least in that the plants who have evolved in a certain area have evolved with this comparative fear factor of the cold and adapted to that and change it. And
that's a really interesting perspective. I think the way that I would see it is maybe flipping it and thinking that you evolved in the presence of snow, which is maybe a mutualist or a helping presence, and now you're left without that. So what happens? And it kind of equates to probably the same thing as what you're describing, but it's just slightly different perspective. That's really interesting. Yeah. Great. Any other questions? All right. Oh, yeah. Yeah. Oh.
Obvious. Have you ever insight as to getting rid of buckthorn?
Yeah, getting rid of buckthorn, it's hard. It's really good at what it does. That's why it's invasive, right? I have a ton of buckthorn in my yard that you can get rid of too. One thing that I've talked to a number of folks about doing that I'll probably try personally here is cutting it down, and then they sell something called a buckthorn baggie, I think is what it's called. You Google it. It's basically that heavy black plastic, and you kind of zip tie it onto the stump. And so when you cut buckthorn down, it just re-sprout basically. So when it re-sprouts, it's sprouting inside this black plastic bag. There's no sunlight and it's really hot and just cooks it. So that's the idea, is to kind of like use that resprouting against the buckthorn kind of. The alternative is like, what's been really effective is you cut it down and then you like paint herbicide on it. Which I think is like, it's fine like in some contexts, but if you don't like, I've got like kids or if you have pets or something, you don't want to put that in your yard. Plastic bagging is like the lesser of the two evils. So, and I think you need like a special license to apply that herbicide anyways, so just put the bagging on would be my recommendation.
Spread through the roots.
Yeah, it shouldn't spread through the roots too much, yeah.
But that's what it is.
Yeah, so I'd say like every time, everywhere that you've got like a shoot is like cut it down and put that back in, yeah. And it'll look bad for a year or two, but like then maybe it'll like resolve. Yeah, yeah. Yeah, well,
About invasive species, I'm thinking more in terms of insects.
yeah,
That are doing an awful lot of damage.
sure.
I'm gathering a lot of that is due to climate change, to them being able to, some of it's due to international commerce, of course, but.
Yeah. Yeah, so we're seeing like there's more and more invasive insects coming here in the first place because of things like international commerce. And then once they're here, things like climate change are amplifying what they do. And so a couple of examples that, yes, I mean, it's definitely true. Things like less extreme or like milder winters, basically, where you don't see a lot of freezing temperatures. It just means fewer of the pests die, because cold temperatures will historically kill them. And then also, when kind of like what we talked about here, when a plant experiences the effects of climate change, it's a stress. Like it might not die, but it's diverting energy that it would normally spending on things like growth or like making chemical defenses, for example, to just like survival. And so now by reallocating those resources away from what we usually spend them on, that's when these invasive herbivores kind of have an easier time because they're just attacking like more susceptible plants. Yeah, so it's a pretty strong parallel of what we were showing with the scissors herbivore.
Have there been any successful fights against some of these invasive? I mean, you can just see swaths.
Yeah.
In every part of the country,
Yeah.
at least out west and here, you see, the forest is just dying.
Yeah. Yeah, that's a great question. And one of the things that's really hard about invasive species in particular is that by the time most of us hear about them, the problem is already so bad that it gets really expensive and really difficult to control it. So what a lot of people are probably doing, and this is something I talk about in my classes, there's a lot more emphasis on like surveillance and like early detection. So things like, using, dogs at airports that can detect, the transport of invasive species. Or looking, you can actually like take a water sample and look for DNA of invasive species to see if it's like there or not. And so there's a lot of investment in that early stopping the problem. So most of the successes, I don't think we hear about. If that makes sense. So I can't really think of like a specific example. I know that I've read about them, but there's definitely, there's not a lot of like splashy headlines for that. But less so on like the big scale of the problem.
On that note.
Yeah.
On the website, the Arboretum website, there's an article about the ash borer, and there's some success being shown with a type of wasp that is helping to mitigate the invasive. So
Cool.
check it out on the website.
Thank you.
Yeah.
And I just want to say thank you everyone for coming, and be looking for our schedule for September.